Okay, in this video we're going to be graphing polynomial functions. And the directions say classify each polynomial function, then graph the function, and identify its key characteristics. So we are going to go ahead and classify. Let me zoom in. We'll classify these first. First off, this is an x squared function, so that would be a quadratic. And we know that a quadratic graph would be a parabola, if you remember from previous courses. So let's do this. Let's go ahead, and since we know it's x squared, let's go ahead and do our end behavior first before we even graph this. And that way we can see if we understand end behavior. So for a positive x squared, as x goes to the right, we know that our y value will increase. And as we go to the left, our y value should also increase. So both of those should be positive infinity. Something else that we can do before we graph is we can also tell whether our domain is going to be. Our domain is going to be all real numbers here. And I'm actually going to use Desmos to graph these. You can use t-tables, but I'm going to use Desmos, and we'll look at the graph from there. So here's our first graph, and we see that it is a quadratic, a parabolic shape. And we have a minimum value here at -1, -6. So let's go back and let's sketch this graph onto our paper. Okay, there's a sketch of our graph. We've got our domain already, our range. Notice your graph starts at a y value of 6 and goes up forever, so 6 to infinity. Your relative minimum was located at -1, -6. There were no relative maximums. So therefore, our increasing and decreasing interval, we start our graph from left to right decreasing, and we decrease from -infinity up to that -1 value. And then we start increasing, and we increase for the rest of our graph. Number 2, y equals -2x to the third plus 8x minus 1. This would be a cubic because of the x to the third power. Now, a normal x to the third power would look like this. However, this one has a negative out front, so we know that that would flip our inequality over, flip our graph over. Or we could just go by every odd power that's negative would look something like a negative slope line. So therefore, our end behavior we can label. As we go to the right on our graph should go down. As we go to the left on our graph should go up. The domain for every one of these polynomial functions will always be negative to positive infinity. There should be no discontinuities. Let's take a look at the graph. Okay, here is our graph, and it is exactly what we thought it would be. We can go ahead and do our relative minimum here. It's going to be located at -1.2, 7.2. And I went ahead and wrote it down, -1.2, -7.2. That's a relative minimum, and I put me a dot on my graph to represent it. We did have a relative maximum here at 1.2, 5.2. So let's go ahead and write that down. And I went ahead and put a dot on my graph for there. So there's your minimum and maximum. Let's go ahead and sketch our graph from our Desmos graph. So there's a picture of our graph along with our max and mins there. Our increasing interval, we see that our graph actually starts decreasing. So let's decrease first from -infinity up to -1.2. Then we increase between the minimum and the maximum, so -1.2 up to +1.2. Then we start decreasing again, and we decrease from +1.2 for the rest of the time to infinity. We didn't do our range, so let's go ahead and take care of that. The range would, notice my graph goes down forever, and it actually goes up forever. So my range would also be from negative to positive infinity. Number 3. We have an x to the fourth graph, so we know that that would be a quartic graph. And we know with a quartic graph, since it's an even power, it's going to follow the same end behaviors as a parabola. Now, the only difference is it might have like an extra heel in the middle. That is the difference. So let's go ahead and do our end behavior. Now, I do want to point out something too. Since it's a positive x to the fourth, now had that been a negative x to the fourth, it would have flipped it over. But as we go to the right, our graph should increase. And as we go to the left, since it's parabolic looking, our graph should also increase as well. Our domain will always be negative to infinity. And now let's take a look at our graph, because now we do know our range will not be the same because there's going to be missing graph down here because of the nature, the look of the graph. So let's take a look at what this will look like. Okay, here's a look at our graph. We do have a relative minimum right here at negative 1.1, comma, negative 1.0. Have a relative maximum at 0, 1, and then another relative minimum down here at 1.8, negative 7.3. So let's go ahead and put those on our paper and label those on our graph. Okay, so I went ahead and labeled those. Now I went ahead and sketched a look at my graph. Okay, let's talk about increasing and decreasing. Well, we can do our range first off. There's no graph below this point. That is our absolute minimum. So we know that our range would be all values from that negative 7.3 and up. So that's the lowest point of my graph. My graph decreases to begin with. So from negative infinity up to this x value of negative 1.1, my graph decreases. Then it increases from negative 1.1 to 0. Then it starts decreasing again at 0, and from 0 to 1.8. It decreases, and then it picks back up there and starts increasing from 1.8 to infinity. Okay, number 4. First off, this is an x to the 5th graph, so therefore that would be a quintic graph, a quintic polynomial. The domain, as always, would be negative to positive infinity. Since it's an x to the 5th power, it's an odd, so it will follow the same end behavior as x to the 1st power, since it's a positive out front. So therefore, our end behavior will be, as we go to the right on our graph will increase. As we go to the left on our graph will decrease. So let's go ahead and look at the graph of that on Desmos. Okay, here we see a look at the graph. We do have a relative maximum, relative minimum, relative maximum, and a relative minimum at these spots. Let's go ahead and write those down and plot those points on our graph. Okay, so there's a sketch of our graph along with our relative minimums and maximums. We can go ahead and take care of the range. My graph goes down forever and up forever, so my range would be all real numbers. My increasing and decreasing, okay, from negative infinity up to this point right here, my graph increases, so that'd be negative 1.5. Then we start decreasing at negative 1.5. And we decrease up to the value of negative 0.4. Then at negative 0.4, we start increasing again, and we increase from there up to 0.4. Then we start decreasing again, and we decrease from 0.4 up to 1.5. And then from 1.5 for the rest of the way, we are increasing. And I believe that would be everything. Next graph, number 5. X to the 3rd, this would be another cubic function. If you don't remember, a cubic function should look something like this. Again, you can go by the x to the 3rd. It looks like a linear, which would be x to the 1st, since it's positive x to the 3rd, except for it's going to have an extra heel in the middle. So therefore, we can use that to classify our end behavior. So as we travel to the right on our graph, y should increase. As we travel to the left, y should decrease. Our domain for our graph, again, is always infinite, negative infinity to positive infinity. Now let's take a look at the actual graph. Okay, we do see that basic shape here with our graph. We have a relative maximum at 0, 2, and a relative minimum at 2, negative 2. Let's go ahead and plot those points and kind of sketch out our graph. And we can see that our end behavior is correct. We increase to the right, decrease to the left. Our range for this function, it has no bottom or top, so therefore our range would also be negative to positive infinity. We did have our relative minimums and maximums at 2, negative 2, and at 0, 2. The function is increasing starting at negative infinity up to this x value of 0. Then it starts decreasing from 0 over to 2. And then it starts increasing again from 2 to infinity. And our last graph, a negative x to the fourth. Since it is an x to the fourth graph, it is quartic. Now, it is a negative x to the fourth, so it's not your normal even function. It's flipped over. So and it'll follow, okay, let's go through the steps. Here's x squared. So x to the fourth will probably be the same with maybe a hump in the middle. Since it is a negative x to the fourth, it'll be that value flipped over. So let's talk about what our end behavior would look like. As we travel to the right or as we travel to the left, both values will go down. They will decrease. So therefore, this is what our end behavior will look like. We can erase these graphs. I just used those to find the other one. My domain, as always, for a polynomial function, it will have no breaks. It'll be everything. So now let's take a look at what this quartic polynomial looks like. And you can see here we have the general shape right. Now it doesn't go up and actually have the extra hump over here, but it is something similar to that. Have a maximum and looks like kind of more like an inflection point somewhere around in here. We don't really have a max or min there. So now let's go back and again label at that maximum on our point, or maximum point on our paper. So it was negative 1.8, 6.4. And that was a maximum, negative 1.8, 6.4. And there was no, again, relative minimums. Let's kind of sketch out a picture of this graph. Okay, so there's you see a picture of your graph, and let's go ahead and label this was my point, negative 1.8, 6.4, which was my maximum value there. So therefore my range, my graph ranges from negative infinity up to the point 6.4. That's my highest y value that's on my graph. So I'm increasing. We start off the graph by increasing from negative infinity up to that negative 1.8. And then we start decreasing at the negative 1.8. And we actually decrease from there forever. So there's the characteristics of my graph.